Okay, here's number 4. Okay, it is estimated that the probability of a win in blackjack is equal to 0.46. You're given odds in favor of winning is equal to 0.46 over 1 minus 0.46, and that's 0.46 over 0.54. Is that good? And that's just going to be 46 over 54. We could bring it to lowest term. 23 over 27, how's that? Okay, so number 4, what did they want here? What must you wager to win $15? Okay, so it's wager over win. So we know 23 over 27 equals wager over the win. And that is wager over the win. Hold it. What must you wager? So cross multiply. So wager equals 15 times 23 over 27. So that was number 4, and that was page 25. What does that work out to be? Thank you. Okay, was that okay for number 4? You wanted 5?
Yes, please. And Miss Kaczynski, I had a question. For question 14, I put the numbers into my calculator and I kept getting math error.
Yeah, I wouldn't worry about 14. I don't like it.
Yeah, so and then some questions I answered yesterday's homework as well, where like I got where I got math error. So will we get those questions on the test?
No. I'll, oh, okay, yeah, we won't have weird answers. Okay, did we want number 5? Okay, you know odds in favor of A equals H over K, but you know that equals to the probability of A over 1 minus the 1 minus the probability of A. Agreed? Okay, so now solve for the probability of A. I'm going to cross multiply. So H minus HPA equals KPA. Right? And then I'm going to bring over the PAs to one side so I can solve for the probability of A. So H equals HPA plus KPA. So far so good. I just added HPA to both sides. Now I can factor PA, and this is H plus K. So probability of A equals H over H plus K. Proven. Number 9? You want number 9? Oh, you wanted number 9. Remo's convinced he's a lucky card player. Shh. He boasts that he can cut a face card 30% of the time. So he's going probability of face. Now this is his boastful 0.3. Oh, okay. How's that? Okay, thank you. What odds would you give him based on calculated probability? So probability of a face card calculated, how many face cards are there? 12? 3 over? So the odds in favor of a face card based on our probability models is going to be 3 over 13 over 1 minus 3 over 13. So isn't that just going to be 3 to 10? Yes. Okay. What odds would Remo be willing to give based on his estimate? So odds in favor of face card based on Remo's estimate is going to be 0.3 over 1 minus 0.3. That's 0.3 over 0.7, which is 3 to 7. If Remo puts down 25 cents based on his boastful odds, so we're going to use the 3 to 7, what do you stand to lose if he wins and does not cut a face card? What?
If he cuts a face card.
If he does cut. Oh, why would they put does in front of that? I don't know. It's, yeah. So it's wager over. He puts down 0.25. So we'll calculate his win, right? 3W equals 7 times 0.25. Whatever that works out to be. Are we good with that? What does that work out to be?
58 cents.
Oh, thank you. Anything else? Yeah.
Question asks, what do you stand to lose?
Yeah, so you have to pay out 58 cents to him, right? Because that's how much he wins. And if he wins, you're the one paying out.
Okay. Press 12.
Number 12? 11 and 12. I wonder why this is so tricky.
The wording.
Oh, okay.
The amount of formulas.
Okay, it's asking you what odds would you be willing to bet to give that at least 2 of the last prime ministers have died on the same day. Okay, I don't know. I don't know how many prime ministers there were.
Sure, we're supposed to calculate the prime minister that have died, or all the prime ministers. Like, and
It's too ambiguous. I would tell you, assuming there were 32 prime ministers, what odd? Yes.
all of them have died.
Yeah.
A lot of the recent ones haven't died yet, so I don't know which ones are we looking at. And there was
Who knows?
so we're not doing that.
No. Who cares? What was the next one? 12. Mrs. Liu asked her finite class of 32 students to write down a random number from 1 and 100. She is willing to wager spares against extra classes that there will be at least 2 numbers the same. So let's probability at least 2 same equals 1 minus probability all different, right? That's the famous birthday problem. So now we're going to go 1 minus 32 students, right? 100p 32 over 100 to the 32. And what do we get? What is it?
3.76. You want the rest or no?
Times, yeah. Well, hold it.
I got 0.996.
I got 3.76. I don't know. Maybe the
0.9962.
Oh, minus 1.
Yeah, so it's very close to 1.
So this is very close to 1.
Very high chance. So you basically say don't take the bet.
Yeah, because the odds in favor at least 2 is going to be 0.9962 over 1 minus 0.9962, which is very high. Her odds are too low. Her odds of 5 to 3 are too low. Yes, I can move a little bit. There we go. Because this is big odds. What's on the bottom here?
No, the probability of her winning is close to 1.
Yeah, they just discussed the probability.
Yeah, you don't. So the answer is you don't take
Okay. So we could have stopped right there.
Yeah, her odds are irrelevant.
So that I was wondering what 5/3. How is that relevant to this?
It's not.
It's not. It's just there.
It's only that number is close to 1, so we should have taken that bet.
Yeah.
Okay.
Should we do it with our
Unless her odds are higher.
our class? Is
Yeah, if
66
the
or
odds were a
60.
lot more extreme, if she put the odds at like 100 to 1, then
Yeah. Like her,
but in this case, it's not even, it doesn't even matter.
it's not even if her odds.
Her odds would have to be higher than 99.6 to
Yes.
1.
For you to take that bet.
Yeah.
Okay.
Oh.
Because if
That's
not,
Oh.
what you get.
So if she offers like 200 spares to like one extra class, you should take it. Because even though your chances of winning is so low, if you don't win, you do one extra class, but if you win, you get 200 spares.
Yeah.
So it's worth the risk.
Yeah.
But not
But in
now.
this
You're a
case,
risky person.
Oh.
but it's not really a risk. It's like one extra class, whatever. Yeah, that would suck. But if I get 200 spares,
Yeah, you just want
Not to go to school ever.
you just want to like to bet in a small probability and win a larger amount.
2 months.
So we, Adrian, what if we do it with our class? It's only 66%.
You should have like efficient market.
why? If I take spares because I have a bet,
Make sure it's not
none of that,
recorded.
I can't be tested on that stuff.
Yeah.
I think I should take one of those.
The date today again? 14? All the best. Anything else?
Oh, well, 14, but I guess we're gonna skip that one.
Yeah.
Then that's it.
14. So we're skipping 14 and 15.
Yeah, skip. If it makes you feel better, just... I did it at one point, and then I saw, what?
Yeah, I got that too.
Wait, can you show us the last question?
You just got a permutation, right?
He's going to for 5D answers. It's only if you do 2 divided by 9. That's how I got the right answer.
Divide by 9.
Yeah. So you know the mistake that I did on my equation?
Yes.
Yeah. If I did that, then I get that answer. But it's not. It's 3
Why?
over
Where
5.
did we get those numbers from?
He got a number by placing the 9
over 11.
I calculated the...
Yeah. That's so we have the odds against. So we have to convert it to odds in favor.
Wait, these are odds against.
Yes. That. The entire question is.
That's what it says, right?
You get odds from it.
It says odds against winning. So you literally change it into flip. Yeah.
Yeah, I wouldn't worry about these two questions, because I would never... I mean, I don't expect you to understand triactor on a... Or... Well... Yep. Sorry? Sorry? Oh, yeah, I should bring in a roulette wheel and we should do some betting in here.
That is really bad. We'll never win. We'll actually never win.
Mahjong?
No, we bring in poker cards on Monday.
Because polar cards are too simple.
Everyone make their cash.
Like hold them up or what?
Okay, stochastic process.
Depending on how many people play. Because like,
Okay, ready? Excuse me. Please remember we're still recording. Okay, a stochastic process is a sequence of experiments like rolling a die after rolling a die after rolling a die that depend on some chance element. They have some probability. For example, rolling a die twice is a stochastic process because each outcome has a chance element to it or a probability to it. Okay, Indira estimates that the probability of getting the next question right if the previous one was right on a math test is 4/5. But the probability of getting it right if the previous one was wrong is only 2/5. If the probability of her getting the first question right is 3 over 4, what is the probability of getting the second right, the third right? Okay, we're going to let A, B, C be the events that, so A, she gets the first one right, B, she gets the second one right, C, she gets the third one right. And then this is the question, she gets A prime, she gets A wrong, B prime, she gets B wrong, C prime, she gets C wrong. So let's draw a nice big tree diagram to help us work this out, okay? So what we're going to do is, here's the, maybe we'll start about here, I guess. On the first question, she either gets it right or wrong, right? On the second question, she either gets it right or wrong. And on this, if she gets A wrong, then on the second question, she gets right or wrong. And continuing, it's going to be C, C naught, C, C naught, C, C naught, C, C naught. Now, they give us a starting probability. If the probability of her getting the first question right is 3 over 4, then the probability of her getting it wrong is 1 over 4. So far, so good? Okay, now, the probability of getting the next question right, if the previous one, I guess her confidence goes up, this is 4 over 5, right? So she knows she got the first one right. It boosts her confidence. She gets the second one right. And the probability of, if she got B right, the probability of getting the next one right is also 4 over 5. So we can fill in this B naught branch, which is 1 over 5, 1 over 5. Now,
Is that 1 over 5 or 2 over 5?
it has to add up to 1.
But get it right.
No, KE, it's because
Oh, sorry.
We're good? Now, the probability if of getting it right if the previous one was wrong, ooh, she's shooken up a bit, so this is 2 over 5. So it has to add up to 1, that's 3 over 5, right? Okay, now if the previous one was wrong, her probability of getting B right is 2 over 5, and this is 3 over 5 because it has to add up to 1. All right. That would be 4 over 5. And what's, and this one's, previous one is wrong. Does that make sense? Mm-hmm.
How the second sentence says, for example, rolling a die twice is a stochastic process. But that's rolling a dice, the outcome of one number is always 1 over 6. It doesn't change. But this one, it changes if she gets depending on her previous answer.
Mm-hmm.
So how is rolling a dice twice a stochastic process? Stochastic process.
It doesn't matter if the probabilities don't change. It's just an experiment after an experiment after.
Oh, so it's like
Yeah, yeah. Just a repetition of experiment. Okay. What is the probability of getting the second one right? It's here, right? And here. Agreed? So probability of A intersection B plus probability of A not intersection B, right, is equal to, well, that's just going to be 3 over 4 times 4 over 5 plus 1 over 4 times 2 over 5. That is going to be 14 over 20, and that is just for, you usually put 1 equal sign per line. That's 7 over 10. Yeah.
In the factor, it's
No, it just wants the second one right. You could do that. You'll still get the same answer. Okay, 2, the third one right. Oh my gosh, we've got to do 1, 2, 3, 4. So we really want the probability of A intersection B intersection C plus the probability of, we need this one, probability of A intersection B not intersection C plus the probability of A not intersection B intersection C, right? A not BC plus the probability of A not intersection B not intersection C. So let's do it. This is going to be 3 over 4 times 4 over 5 times 4 over 5 plus, sure, 3 over 4 times 1 over 5 times 2 over 5 plus 1 over 4 times 2 over 5 plus 4 over 5 plus 1 over, did I screw up?
You know how you have the second last one?
Should be times
4 over 5 is times.
Oh, this one?
Yeah, that one times.
Thank you. Plus 1 over 4 times 3 over 5 times 2 over 5. Plug that in your calculator. You will get 68 over 100, and that equals 17 over 25. I just want to point out something to you, that all these things on the branches are conditional probabilities. So for example, this one, this is the probability of getting B right given A was right equals 4 over 5, right? Do you see that? So the probability of getting C wrong given B was right, oh, there's going to be 2 of those. It's going to happen there and there, right? So note that these probabilities on the branches are conditional probabilities.
That one's 4 over 5. By the way.
Okay, so that would be probability getting 1 over 5 plus, where do you get 4 over 5?
B given A. The question before, it's 4 over 5.
Oh, thank you.
guarantee for it to actually get.
It would be nice, right?
Impressive, yes.
But the probability of C naught given B was right is going to be 1 over 5. I don't like that. I'm going to just say, no, it's just 1 over 5. C right given B was wrong. No, C right given B right. No, C wrong given B right. C wrong. Yeah.
Always 1.
Yeah.
But because there's different kind of probability that B can be right, so we need to add up. So it's numbers.
Yeah.
Wait, so it's not 2 over 5?
No. This is the probability C is wrong given B is right.
That never changes. No matter
But if you want, yeah.
Just like B can be
because
different way.
C depends on if B is right or wrong, but B depends on A. But C doesn't directly depend on A. C
No.
depends on B and B depends on A.
Yeah,
C
yeah.
doesn't depend on A.
Yeah. Good. Do you want to do the first homework question together, because it's really confusing?
The first
The first one is really confusing. Number 1. Andrea and Ling are evenly matched tennis players. All right. However, each time Ling loses a game, so I'm going to put either Ling wins or Andrea wins. They want a 3-game sequence. This is number 1 because we're doing it because it's a little bit tricky. Okay, so this is Ling, Andrea, Ling, Andrea, Ling, Andrea, Ling. Either Ling wins or Andrea wins. Andrea and Ling are evenly matched tennis players. However, if they're evenly matched, that means they start out at 0.5 each. Whenever Ling loses a game, the probability of her winning the next game decreases by 0.2. So this is going to be 0.3, right? 0.5 minus 1/5 is equal to 0.5 minus 0.2, which is 0.3. Yeah? Went into sleep mode.
So that means the chances of was it Andrea winning if she wins her first game is 0.7.
Yep. Absolutely. Now, if Ling loses a game, the probability of his next game is oh, did I screw that up? Oh no, he loses. If he wins,
It increases by 0.1.
so this becomes 0.6, and this is 0.4. So this increases by 0.1, that's 0.7, 0.3. Now, here he lost, but this is the tricky part. He loses, it decreases by 0.2. So what you have to do, his previous probability was 0.6. It decreases by 0.2, so that becomes 0.4.
Oh, yes.
Yeah. Right?
Because in the previous one, the probability of him winning was 0.6.
And now it's
0.4 isn't his probability of winning, but the probability of him losing. So that's why you don't use 0.4 to decrease.
yeah, you use this one. Okay, so here Ling won. Yes, because it's going to be, his probability was what was it? 0.3? Yeah. Oh, you add 0.4, you're right. And this is 0.6. Yeah, this is going to be 0.9, 0.1. Do you see how hers is every time she wins it goes up by 0.2? So he lost, so 0.3 minus 0.2 is 0.1. It kind of falls in.
So how are they evenly matched tennis players?
Well, they are here.
It's just that
It's the starting point.
loss changes.
Things.
Their tennis abilities,
Yeah.
Emotional.
I guess.
They get shook up.
Because technically, if they're evenly matched, then all their chances of winning should be 1/5.
But then you're
Only their first game they're evenly matched.
Yeah. So yeah.
You realize that Andrea, or what's her name, Andrea is better than yeah.
Okay, so that's our tree diagram. Well, find the probability Ling wins at least 2 games. So she's won there, 2 games there, 2 games there, 2 games there, and that's it, right? Probability Ling is greater than or equal to 2. Agreed? probability L, Ling wins at least 2 games. So it's 0.5, 0.6, 0.7 plus 0.5, 0.6, 0.3, 0.5, 0.6, 0.3 plus 0.5, 0.4, 0.4 plus 0.5, 0.3, 0.4. And if you were to work that out, you should get 0.44. And I think you can do the other one. Andrea wins exactly 2 games. So she won exactly 2 games here. Exactly 2 here. There's 3 ways she can win exactly 2. She gets exactly 2, so we've got 0.4, 0.5, sorry, 0.4, 0.6 plus 0.5, 0.3, 0.6 plus no, 0.5, 0.7, 0.1. I think it was just tricky because you have to realize how to read off the next win. Yeah. The original tree diagram was difficult. Yeah. So there, I did your first homework question.